students of physics. There are a whole set of problems where both energy and momentum can be conserved, are conserved, if you're willing or able to look at the right transitions between instants. All right, now, a typical diagram on an exam, I don't know if it would be this thorough, but what I'm doing here is showing what's called a ballistic pendulum. So a pendulum that's made to swing up in the air by the means of being hit with something. So this is like, a little, let's call this a little, bullet or something that hits a pendulum bob. And in this case, we're saying that the bullet embeds itself in the pendulum bob, and then that system swings up to some maximum height. I guess we'd probably assume that is. So the question is, how do you do this? How do you analyze this thing when there's so many different instances to talk about and so much going on? Well, what will be good if you can do is if you can start to identify some different instance that you can call initial and final instance with some different kinds of analysis. And so what I'm going to define here is there's sort of an instant right now, I'm going to call it instant 1, where our bullet is heading toward our pendulum. All right? An instant 1 can be anywhere between now and between the instant when the bullet is like, right here, just before the interaction, moving at, perhaps that speed v. But certainly when the bullet's back here, we're going to assume it doesn't slow down, before getting to the pendulum bob where I've drawn it here. So anyway, that's a reasonable, we can say that instant I've identified as instant 1. And then instant 2, we would say, is like right now, where the bullet has, just finished its interaction with the bob. Now, would the bob really still be motionless? Or, I guess, would the bob really still be, the pendulum, would it still be vertical like this? It probably wouldn't, right? We would say that the bob would, while this interaction happens, the bob would start moving. So we're making sort of an idealized case here of this interaction. But, this is when the two objects have gotten to the same speed. That's my instant 2. The two objects being the bullet and the bob. And then there's this instant 3 where the system has gotten to probably what I'd call a maximum height. Instant 2, we're probably going to assume this is like a V max of the system. All right. And so what do you do here? How do you attack this? Well, again, we don't have anything that allows us to really look at 3 different instants in time, but what we can do is say from one instant to the next, what's the appropriate analytical tool? All right. And so in this case, we do have our, if we look from 1 to 2, well, 1 to 2 is the interaction of 2 different objects. It's a collision. In this case, a collision where objects hit and stick, or what we call an inelastic collision, a completely inelastic collision. Perfectly inelastic? Sure. And so, that is a conservation of momentum example, I guess. All right? When 2 objects interact, the appropriate thing to apply is conservation of momentum. Mechanical energy is not conserved because there's almost definitely some heating up of both of those objects when they're doing all that rubbing against each other, especially as the bullet's like sliding through that pendulum bob. There's a lot of friction going on there that's slowing the bullet down and speeding up the pendulum bob. It makes some sound, certainly, when those 2 things whack into each other. So a lot of sound energy, a lot of thermal energy. Those come from, those take mechanical energy away from the system. So But regardless of any mechanical energy that's lost, momentum is always conserved when two objects interact. All right, and then we have our instance 2 to 3 here, where this system trades speed for height. All right, and in that case, the proper approach, the proper analytical tool is to say that, well, mechanical energy is conserved. All right, we're going to, of course, neglect the effects of air resistance, I'm sure. Oh, we are. And so, you know, this is no longer really two objects interacting, but it's a system where one form of mechanical energy is converted into another. Fair enough? So these expressions can certainly be expanded to things like M1 V1 initial plus blah blah blah, and this can be expanded to 1/2 MV initial squared plus MGH initial blah blah blah. All right, but the important thing is maybe not so much the nuts and bolts, but what's the right principle to apply in each set of instants. And really, the whole thing about identifying different instants that hopefully leads you to the proper tool to use. So the ballistic pendulum is a pretty classic physics example. A couple other ones that I just sort of randomly made up. Here's a situation where we've got, how about this? We've got instants that we care about are like, here's like instant 1, an object up there. Here's instant 2, objects before they interact. Here's instant 3, objects after they've interacted. All right, and then you can do things like say, well, what's the appropriate approach to relate instant 1 to instant 2? Well, that's a system that's traded height for speed, right? We probably say this is at its max height. This is probably, V max right now. V max of, this is object 1. It's a 1. Right, well, that system's traded height for speed, so that's a pretty standard mechanical energy conservation thing. And then from 2 to 3, well, this is before two objects interact to after they've interacted, so that's a net momentum. Now, what I haven't mentioned is when we just say, final and final, that's not the same instant, right? Notice that final in this case is instant 2, and that becomes the initial instant in our 2 to 3 transition. All right, so you've got to be willing to look at, time progress from one instant to the next, where this instant, is both a final and an initial. It's the final in the 1 to 2. It's the initial in the 2 to 3. Same thing with our ballistic pendulum, right? Well, there was, instant 2 is the final instant of the two object interaction, but then it's the initial instant of the pendulum swing. Here's this one where two objects, here's an instant right now prior to interaction. Here's an instant a little bit later, just after an interaction. And here's another instant later on. All right, so from 1 to 2, that's prior to interaction and after interaction, so that's a momentum. And then 2 to 3, well, that's a system trading, well, it has height and speed, but then less height and more speed, so there's changes in amount amounts of mechanical energy, relative amounts of different kinds of mechanical energy from one instant to the next. All right, here's another one. I realized, oh, now this one is supposed to involve, imagine like a compressed spring and then a loosey-goosey spring. I wanted to be sure that not every one of these problems is about a perfectly inelastic hit-and-stick collision. Sometimes they do that just for convenience sake to make things maybe a little bit easier, but it doesn't. There's no requirement. So here's one where we have, how about this? We've got this as instant one, and then we have, this as instant two, and then we've got this as instant three. And so, like from 1 to 2, well, that's an energy transformation, right? The spring's energy, we'd probably call this as like, well, it's not K, but X. Probably say that this spring is at max compression, right? And then there's some what I would used to call Vmax here for that yellow mass. So from 1 to 2, that's a mechanical energy, right? The spring's elastic potential energy turns into the kinetic energy of that yellow mass. And then from 2 to 3, that's prior to and after an interaction between two objects, right? So that's momentum equals momentum. Okay, so how do you know? When do you do? How do you know which one to do? Well, I mean, is there a single answer to this? Probably not. But the patterns certainly are. Momentum. That's the easier one for me to know when to use momentum. Momentum is always conserved all two-object interactions. So the deal is, you got to say, is it about two different things before they interact and after? All right. The multi, does it have to be two things? No. I should really say, is it about multiple objects? All right. And not only that, but is it about multiple objects interacting? Interacting meaning applying forces to each other, right? Starting apart and then sticking together. Starting apart, bumping into each other and coming back apart. Starting together, pushing off of each other and coming apart. Right? Those are all ways that objects can interact. All right? But it's got to be about multiple objects. How do you know when to use energy? Well, energy is usually about a single object or system of objects where some sort of energy transfer happens, obviously, I guess. But, what kinds of energy transfers could happen? Well, lots of them, right? There could be, trading height for speed, or vice versa. There could be trading spring. Well, there's probably a better way to do this, right? I mean, there's basically energy associated with three different main elements, right? There's height. There's speed. And then there's spring And so there's some sort of crazy flowchart here where, you know, this is impossible, but one of these could, speed could turn into height, or speed could turn into spring energy, or spring displacement, or height could turn into speed, or spring displacement could turn into speed, or spring displacement could turn into height, or height could turn into spring displacement, or one of these could turn into, speed could turn into both some height and some spring displacement, or height could turn into both. So there's, but the bottom line is, if there are relative changes in the amounts of these things from one instant to the next, then that's when we use mechanical energy conservation. All right, but this is about either literally one object, or maybe it's like we said, our ballistic pendulum thing is now a system of objects that swings up to here. So that's not a two-object interaction. These two objects are not pushing or pulling on each other while they swing as a unit, right? But they are certainly trading speed for height. Okay? So, nothing new in terms of the actual techniques, right? Where we say ME initial equals ME final, or we say net initial momentum equals net final momentum. But now, hopefully we are equipped to try to figure out when to use these things and really analyze some more challenging situations. Okay? My folks will have some problems to look at with these soon. See you, folks.